All right, welcome back, everybody. This is William Briggs. We're on class 13, not episode 13, season 1. No fair dice. There are no such thing as fair dice. And finally, we move to the symmetry of individual constants from which we deduce the statistical syllogism. And it's the statistical syllogism that allows us to assign, finally, numbers other than 0 and 1. Remember, all we've done so far, at least mathematically, we've done a lot epistemologically, but for the math anyway, all we've done is proved that probability has a certain functional form. That functional form happens to be Bayes' theorem. And we've only proved that assigning probabilities are possible in two cases, two numbers, 0 for falsity and 1 for certainty. We've proved all that, but we haven't proved, last week we did a little bit, we talked about the statistical syllogism and how certain states can be assigned probabilities. And I promised you finally at long last to get to the proof of these things. We're going to do that today. I'm going to leave a little bit of the math out in the most difficult cases, and I'm going to copy it on the blog. I've been giving you all of my books so far. You haven't missed any of it. And so you can read all this stuff in its glory and read the more difficult mathematics. And those involve concepts which we haven't got to yet. Maybe we'll revisit them, and probably will when we talk about parameters and probability models. So first of all, though, we had the homework. We had as our premise that we had a Metalunan interocitor. And that interocitor, I'm going to change states. I'm going to change states using the letter M here for a good reason. That had a certain number of states. It had states 1, 2, n states, in which another premise was that n was definitely less than infinity, which is absolutely we're not going to talk about infinity today, but I'll give you a little hint. There's absolutely nothing wrong with deducing probability discretely and then moving to the continuum in the limit when we need to. But all those will just be approximations because there's nothing that is actually, and I'm using this in a metaphysical term, infinite numbers of contingent things, but there could be potentially, and we'll have to talk about the difference between actuality and potentiality and everything. But for right now, it's absolutely no bar to us to suppose that this interocitor has these potential states and must take one. Must take one. And we wanted the probability that it took, I think, 6. And I revealed also that n equals 6. And so this becomes a Metalunan die, a dice, one half of a pair of dice. And I ask the probability, what's the probability? I'm going to just call all this our evidence. What's the probability that M6 is true given our evidence? Well, using the statistical syllogism, we have 6 states, 1, 2, 3, 4, 5, 6, and there's nothing in this evidence to distinguish them. And as Hempel and others have said, if you can't see that, then there's really not much we could do to convince you. So now what we're trying to do is we're trying to assign numbers to these probabilities. The obvious answer is 1/6. And we're going to deduce that a little bit more carefully, and I'm going to show you attempts by Jaynes and discuss an attempt by Diaconis, Percy Diaconis, that I think fail. And I think David Stove came closest to proving this through something called the symmetry of individual logical constants. And we'll get to that. So first of all, perhaps there's some dispute in this, but we just have this. This works for real die, and it works for Metalunan interocitors, even though there are no such things as Metalunan interocitors. This is, remember, every time, I cannot emphasize this enough. If I have one thing in this entire class, start to finish, if you remember only one thing, it is this: all probability is conditional on the evidence that we assume is true. We assume the evidence is true. I cannot stress that strongly enough. Assuming this evidence is true, what is the uncertainty of this with relation to that evidence? And here we say 1/6. And again, you may dispute that, but by the end of today's lesson, you won't. But the homework was to do that, and then also this. We're going to do the same thing, and we're going to add, well, I guess Boolean algebra. We'll do that. Fair. And that's what I wanted to know. If we added this extra bit of information to our premises, what would this probability be? Well, a lot of people instinctively say fair. But what does fair bias? What does it mean? What could fair possibly mean? It could only mean that the probability of M6 given fair is 1/6. And then we want the probability of M6 given the probability of M6 given fair is 1/6. And this whole thing equals 1/6. This is going to be something we're going to call, and we're going to go over this again, the principal by, I think it was David Lewis who came up with this. Fair asserts what it seeks to prove. Fair says, well, each side is equally likely. What does that mean, equally likely? Look, I have a real die here, a real die, not a Metalunan interocitor. It has 6 sides. Are they symmetric? How do you know? Can we measure it down to the quantum level? To the individual neutrons and protons and electrons that make this up, or down to the quark level, or down to the string level, or whatever is supposed to be down there if you buy strings, or whatever you buy. How can you prove that this is symmetric? If fair means symmetric, this thing will always be asymmetric. We'll never be able to know it's symmetric. We assume, if you like, symmetry is induced from these premises. We don't measure it in here. And even if and obviously we don't have symmetry because we have 3 dots here and they're dug out of the, I guess this is plastic, most of them are plastic, here, and we got 5 dots dug out here, so we have an asymmetry in the weight distribution of this thing right here. So what could it possibly mean? And we're going to have a toss. You won't be able to see this toss here. Maybe I could do it here. So 3, I got a pair of 3s. Good luck. The die comes off my hand in a certain way. It has a certain friction against my skin. There's a certain moisture level here. There's a certain gravitational field. There's certain wind around. This surface has varying levels of friction. It might be different than yours. This is certainly bumpy and not at all smooth. It comes down and it has a certain spin when it hits the ground and moves, all that kind of stuff. We can go on and on and on like that. And what you're asserting is you have somehow, when you add this fair here, perfectly certain circumstances which you sort of close your mind's eye to. I don't even know what fair means. I'm just going to say it is fair. That means it will come up 1/6 at a time every time I toss it. And you're trying to think like a frequentist. If I toss this thing an infinite number of times, infinite now, perfectly 1/6 of them will be M6, 1/6 will be M5. This is the wrong way around. You're thinking backwards. You're not thinking about how probability is deduced with respect to the evidence. Instead, what you're trying to do is you're trying to think of how this model, this is a model now. We can think this is exactly what models are. It's no different. This is a model now of a real die. And how might we apply this to real die or real dice? And so I thought I had this to hand, but I didn't. I have a video. I'll link it in the class. This right here is a coin flipping machine. You put a quarter, American quarter here, and this is part of it. This goofy thing at the end right here. And you put it here and you flip it. It goes up in the air and flips around. And if you start it with heads, it'll end heads every time. It's a fair coin. In whatever sense that could mean. It's a coin that has 2 sides. There's a eagle on one side. The one I used, I guess, is an old-fashioned one, and a head on the other, and bas relief. And you flip that thing, and boom, over it goes. The reason it comes up 1 or heads every time is because I have controlled all the relevant causes. I have controlled all the relevant causes that go into the flip of this sort, and I can make the coin do what I want it to do. So the probability based on the premises I have in this contraption my dad and I built last summer is 1. The probability of heads is 1, or the probability of tails is 1 if I flip it over. And it's the same thing with the coin. The die. All we're doing is measuring our uncertainty here. And if you still don't buy that, which you should by now, because it's all about causes of real things and ignorance of in a model are not the same thing. If you don't like this, then put this. I'm going to put the words unfair here. What's the probability we get a 6 given this standard evidence here? And now I have an unfair die. Just this evidence. You are not allowed to go in here and say, well, I think he cheats with 6. Or whatever you like. Whatever is in your tormented mind up here. That doesn't go up here. That's not part of E. You don't get to insert that up there. You don't get to insert what you like up there. This is what E is. This is what we have. That's all you get. That's the way probability works. You can't just willy-nilly stick things in here. Then you end up like a subjectivist, and you're going to walk around like that Yadowski guy or the Scott Alexander. I'm a rationalist, and Bayesian theorem is all there is. That's nuts. All right, we don't want that kind of thing. We want to think in terms of substances and powers that substances have and causes and all that kind of thing. That's how we're going to do our science. Here, and probability is just a measure of our ignorance, of our uncertainty. That's it. Nothing more. Simple as that. What if we add unfair? What do we get? How does that change the probability? I'll leave that as our homework. I'm not going to solve it for you. I'm going to leave that as our homework. You leave this unfair. You think about that. We'll discuss it next time. Now, what we're going to do is I'm going to erase this. I'm already halfway through this thing. There's no way to get all this. You know, I'm hoping to, maybe all we get to is just Jaynes's. I'm going to show you why Jaynes. Now what we want to do is we had the statistical syllogism. The statistical syllogism was we had states like M1, and I'll use Boolean algebra now, notation, 2, or M3, or Mn with, this is our only real requirement, that. That's it. And we want to know, and this evidence asserts one and only one mi must be the result, if that's our evidence. And then we want to have the probability of mi. So that's one way to write it in this logical form. Another is here, and I'm going to call all this evidence again. And the statistical syllogism says the obvious. We got n states. This is one of them. 1 over n. So we've assigned a number to this. Now, this is dissatisfying in a way because it could be that this one gets, you know, there's n of them. This gets 90% of the probability, some people think. And the 10% that's left is apportioned to the other n minus 1 states. Or however you like. There's any number of possible combinations. The only thing we can gather from this, you remember, is that the probability won't be in the set 0, 1, because this implies contingency. The mi will not be certain, and it won't be certainly false. That's the only thing we could really get out of this for numbers-wise. That much we've deduced so far, just because it's contingent. And so what happens here? So let me give you Jaynes's argument. So the reason this is important is because we have to jump ahead in the math to explain why people are wanting to do this. Not just because they want to prove what things can take, but because of another thing that leads to people thinking they're Bayesians as opposed to frequentists and all this kind of stuff. We're just going to call ourselves probabilists, or if you like, logical probabilists. We're in neither of those camps. It is because Di Finetti has a proof. It's a representation proof based on a little trick we're going to try right here. That if you had an infinite number of variables, mi, that are in themselves, they can take either 0 or 1, success or failure if you like, yes or no, true or false, however you want to do that. If we had an infinite number of them, then there turns out to be, in a parameterized probability distribution of these things, and we haven't even talked about parameters yet, there turns out to be a representation of them, a unique representation of the probability distribution of these things, a parameterized probability distribution of these things. And that's how people end up, that's how the Bayesian sort of revolution happened again in the very late 70s and throughout the 80s and so forth. We have to talk about all that. There has been attempts, like Percy Diaconis, he attempted to do the same thing, and this is in the book, using finite. Di Finetti's representation assumed that n goes off to infinity. Now, infinity is a very strange place. I've written about this many, many times. Infinity is not just a place. It depends on how you get there. It depends crucially on the path you take to get to infinity. And you can end up in wildly different spots inside infinity. Jaynes understood this. Jaynes therefore tried a finite proof, and so did David Stove. I don't think I'll have time to get to David Stove's proof, which I think is the correct one, but I will show you the proof that Jaynes attempted. So let me keep this up there, and you have to remember all the rest. Let's see here. The evidence remains the same. One and only one. So that we want to calculate the probability, the entire distribution, M1 or, I better put the M2, M2 or Mn given this evidence. So that's what we're after. The entire probability is going to be 1. We know this because the evidence says one and only one of these must happen. So this is absolutely true that one of these states, given this E, it's a model now. It's a model. It's not reality. It's our understanding of how we might apply this to something. You must always keep this in mind. You're not allowed to say, well, a lightning bolt comes down and strikes out M3 from this. Had you thought of that? None of that stuff applies here. This is only the evidence that we assume and nothing else. All right? You absolutely have to keep that in mind. That's the entire lesson of the class. Start to finish. Change the evidence, change the probability. Simple as that. Change the evidence, change the probability. All right? I should have just called the entire class that. Change the evidence, change the probability. Well, this should be, whatever this is, this should be equivalent to, let me do this. And for some reason we like to use this kind of notation, and or m pi 2 or mn given e. This is a permutation of indices 1 and 2. So in other words, pi 1 equals 2 indices from this first bit up here, and pi 2 equals indice 1 in this bit of evidence up here. Jaynes put a little bit of a, I think he used capital M instead of E. It's in the book. It doesn't make it, this is a problem with notation. We've talked about that many times. I won't dwell on it now because there's no point. It doesn't matter what notation I use here. Because we don't know the value here of M1 and we don't know the value of M2, the probability values here, remember this is our goal, to try to assign a probabilities. We're trying to see if we can get away with, or find some way we could deduce what these probabilities would be. And it should be the case that because we don't know anything about these states, the only thing we know about these states is given up here. We don't know if this is a die, we don't know if these are dinosaurs, we don't know if this is UFOs, nothing. All we know is we got these states, and only one, and one must obtain. Somehow. We're not saying anything about cause. Therefore, the order that we consider them doesn't matter. That much we can induce, or we deduce from, whichever way you want to think about that, from the evidence that we have. So this one should be equivalent to this one. And now comes Jaynes's trick, which I think fails. let me erase this permutation. This pi kind of notation is used all the time, and you'll need it for the reading the homework, reading the book. That's used all the time. Why, I don't know. Perhaps p, pi, permutation. In any case, I think that's what Diaconis used, so everybody uses it. All it means is just a switching up of the indices. And later on, we'll talk about techniques like MCMC, Markov chain, Monte Carlo, and bootstrapping, and all that kind of stuff. All we do is mix up the indices that we have. It's just a mixing up of the indices. That's it and nothing more, but it sounds fancier to say permutation, I guess. Basically, in the end, what Jaynes deduces is that probability of M1 given E is going to equal the probability of M pi 2 given E, and the probability of M2 given E is going to equal the probability of M pi 1 given E. And from that, as you could see, if we can mix up these indices in any way we want, I'm not going to go through the whole proof, you'll read it, but you get the idea, I think, here, because I can mix these indexes or indices up any way I want. It has to be that there is a symmetry here that I can use, and so I must be able to have mi is going to equal 1 over n. But I'm going to read to you, I'm going to read this out loud to you, how Jaynes made this trick. And without dwelling on the absolute steps of the math, it's in Jaynes, chapter 2. I'll have the links on the blog, which are all down there. And I have it in my book, and that'll be on the blog in the written lecture. And you can find all that. This is his trick. And let me read you this. He says, Jaynes makes the crucial step, which is to add to this evidence, which states that the total evidence is indifferent. You'll see this word used a lot. Indifferent. The evidence is indifferent to M1 and M2. The evidence is indifferent to M1 and M2. That is, here's quoting Jaynes now. If it, the evidence, if it says something about one, it says the same thing about the other. And so, this evidence contains nothing that would give us any reason to prefer one over the other. And so he comes to this equal probability thing right here. But I trust you could see the circularity of this argument. He assumed indifference and then concluded indifference. He added indifference here, and then of course we conclude indifference here. Well, we should, because it's up here as one of our premises, and if we're assuming indifference, we darn well better get it out of the conclusion too. So he does. Percy Diaconis has a proof of this in the same kind of a way, and there's no way I'm going to do this for you. It is a he uses permutation groups and binary expansions of indices and all this kind of stuff. I have all the gory detail in my book, and I'll put that up for you to look at. But it involves the same thing. In the end, what he did was there's a certain number of coordinates in his binary expansion of these m's. And he assigns those things. It turns out that there's, I think, n choose n of them. It turns out that there's n choose, and we haven't even talked about what choosing means or anything like this. So, but this is a combinatorial calculation, n choose m. It gives you a certain number, an integer number. And so he says, well, assign weights 1 over these to them, and then he works through the proof, and then he finds basically the same thing. Well, this is again asserting indifference, as you'll see in his attempted proof. It asserts indifference inside the premise, whereas we want to prove that. Like I say, the only one who's come close to actually getting this is David Stove. He uses a better, tighter, and simpler. We don't need all this sophisticated math and everything to get us there. He uses the symmetry of the logical constants themselves. We focus on these logical constants and see what we can get out of them. And there's a certain, you can see right now there's a symmetry. I don't know anything about M1 versus M3 versus M2 versus M3 and so on. They're just states. I don't know what these states are or how they come about or nothing like that. So I should be able to move those around, and that's how that proof is going to go. And then we do get to the statistical syllogism. Then we do come up with these assignments of equal probability, and we finally have numbers assigned to probability that are other than 0 and 1. And there we go. Now probability is a number between 0 and 1, 0 meaning locally or conditionally false, giving our evidence. Here we go. Right there. 1 meaning conditionally or locally true, given our evidence. And other numbers meaning the amount of uncertainty with relation to the evidence that we have. That's it and nothing more. There's nothing about frequency. There's nothing about being Bayes and subjectively thinking about these things one way or the other. And we're going to explore all those ideas in great detail. It's just a simple matter of the amount of uncertainty we have given the evidence we assume is true, and not adding anything extra to it and try to get around this or anything like this. Okay, so that's it. Next time we will do stove, and your homework is, again, maybe I'll just write it up here so you see the homework. Let me just write it up here. We did this. We did the probability of M6 given the standard E. That we all agree. Now, assuming Stove's proof holds up, we have 1 over 6. Then we did probability of M6 given fair. This just becomes a circular argument. We assert the probability is 1/6 in here. This just asserts it, and so we better darn well come up with 1/6. And now I want you to, I gotta get this board pinned on here better. Unfair. That's it. This is what you have to, oh, that looks like a 7. Let me get rid of that. How about that? Is that a better question mark? That's it. This is your homework. Discuss this. And next time we'll do Stove, do his proof. Then we'll move, we're already in Jaynes a little bit. Then we're going to move back into Jaynes and start, because we've done this, that's it. Now all of mathematics is available to us. We're off to the races. We can start going crazy. We can use this combinatorics. That'll be our first stab at probability, because life is easier when you're finite. In fact, just as a tease, life is a lot easier when it's infinite. The math, once you start using the continuum, you're using calculus and the like, that's real easy. Counting is hideously difficult. Oh my God. Just trying to count, that we already saw with the Monty Hall question and all these other kinds of things, how difficult counting can be. And then some of these cases and so forth, it's just easier to assume that n flies off to infinity, and we can get things in an approximate form, and there's nothing in the world wrong with that. In fact, it's absolutely the right thing to do, as long as you remembered you did it. And here's the sad part. Most users of probability and statistics have forgotten that's what was done. And somehow these infinite models are reified. The deadly sin of reification happens, and their models become reality, and we have all these difficulties we're gonna get to. This is the really exciting stuff. Now we have all this kind of stuff proved. And if you don't believe it, go back and read. You have 12 lessons to go back and read. We're just going to be able to go to town with the math now. The stuff that everybody wanted to get to will be there, and then we can really start to learn how all this stuff is used in science and how it's increasingly misused. How about that? I'll put it that way. That's it for right now. All the links are down there, and people who have questions about the homework and so forth, I will answer next time. Thank you very much for listening. Bye for now.